Hi everyone, I'm Matthew Kerr. I've been a scientist with the LAT collaboration for about 14 years now, and I work primarily on pulsars, specifically pulsar timing, but also on how they emit light from radio to gamma rays. Today I'm going to show you how to analyze pulse signals in Fermi-LAT data. Perhaps you too want to study pulsars, or perhaps you have a bright source that happens to lie near a pulsar, and you would like to remove as much as possible the signal from that pulsar in order to get better signal-to-noise ratio on your source, which can help a lot. So first, of course, we've got to get the data, and I have gone to the Fermi Science Support Center's data access site, where you can find all sorts of data products. We want the LAT data server here, and we're going to look at data from the Vela pulsar, which apparently I've typed before. It's the brightest pulsar in the gamma ray and radio sky. Let's get about 5 degrees worth of data. We're going to get the whole mission, so we can just enter these keywords like this, and then let's put in a notional data range of 100 MeV to 30 GeV. Let's click Start Search there, and it tells us that our data will be ready in about 3 minutes, so I will see you then. Okay, so it's been 3 minutes, maybe a little longer, and this is the results from our query. You can see it's generated a number of files, underscore SC file here. This contains the spacecraft position and attitude over time, and then a number of pH files here, which contain the actual event data. We typically refer to these as an FD2 file for the spacecraft file and FT1 files for these photon files. And I have followed the advice here and in a separate terminal window executed these wget commands to download the data. So, on to the next step. Okay, so here are the data where I've downloaded them in this particular directory, and I would like to merge these individual photon data files into a single FITS file and also do some rudimentary filtering on them. So the first step will just be to make what we call a meta file, and what I want to do is get all of these photon files and merge them. So I'm going to just put their names in this file here called FT1 list. And now when I invoke GT-select, and you'll notice that I'm in my Conda Fermi environment here with all the Fermi tools set up. When I invoke GT-select, I can put an @ sign here and FT1 list.ask, and it'll read all of these files in. And then for the output, I'm just going to put let's do Vela merged. And if I leave these undefined, it won't apply any new cuts. I'm going to keep all the time and position. It will, on the other hand, change my energy cuts, so I want to re-enter those. And let's pick a maximum zenith value of 105 degrees, which will cut out most of the background from the Earth's limb. So I do that, and the merging will start to happen. And catch you in a few minutes. Okay, we're back. The GT-select command has finished, and you'll see that these files here have all been squished into this one single file, Vela merged. And if you look at the file sizes here, you'll see that it's substantially smaller. This is because we've discarded all of those photons that were more consistent with coming from the Earth limb than from the sky. Alright, now that we've merged our data, the next thing we want to do is inspect it. And there are various Fermi tools to allow you to do this, to make counts maps of the sky, and they're really the official tools, so you should use those. They're well documented, however, so I wanted to show you kind of a quick and dirty way to get at the data more directly, just using Python and AstroPy. So if you have a Conda environment, it's very easy to install AstroPy, so I suggest you do so. It's very helpful. And we're of course using the Vela pulsar, so here I'm using AstroPy to get its coordinates without having to look them up myself on Simbat or something. The first thing we're going to do is load the data. So here is just using the AstroPy FITS library to open the file. And this is a pretty standard FT1 file, and it's just got columns and a series of tables, and there's an events column that tabulates for each event reconstructed by the Fermi-LAT various properties of it, including its right ascension, declination, measured energy, zenith angle, etc. Feel free to inspect that. In fact, maybe I'll show you that later if I remember. If you've done this step, it will also have a column labeled pulse phase, which in principle tabulates the spin phase of a pulsar, so where it is in its rotation. We haven't gotten to that step, so I'm just going to leave that commented now and return the value of none. That's how we get the data out. Now what do we want to do with it? Well, there's this little function called make counts maps that I've written. And first we call that load, whoops, that's the wrong name, I changed it. Event data. We'll load the data. And then the next thing I'm going to do is cut out all the events that are less than 1 GeV in energy. This just makes things a little bit quicker and also yields a better point spread function for us to see what's going on. Next we use AstroPy to define sky chord objects for each our right ascension and declination. And the reason we're doing this is because we want to convert to galactic coordinates. So here we're defining both the position of the Vela pulsar in galactic coordinates, and we're converting every single photon reconstructed direction into galactic coordinates. I've defined that mask twice, so I can probably get rid of that one. And here we have bins that we're going to use in our sky map. So because we're using galactic coordinates, and because Vela is pretty close to the galactic plane, we don't need to worry about projection effects. So these are simple uniform bins in galactic longitude and galactic latitude. So on to plotting the sky map. This is Matplotlib, Matplotlib, which many of you are probably familiar with. We're just going to first do a 2D histogram of the galactic longitudes and latitudes using the bins that we've defined, and we're going to use a log normal scale, sorry, not a log normal, we're going to use a log scale, this is just the way that it's defined in Matplotlib, because the dynamic range in our data is relatively large, it's about 4 orders of magnitude, and we're going to use these keyword arguments to trim out some of that dynamic range, just so we can see a little bit better what's going on. We add some labels as we're supposed to, and then the other plot we're going to make is a particular slice of the data along one particular line of galactic latitude, and you'll see why in a second. So let me go ahead and run these commands and let you see the results. Okay, so I've just run make counts map, and that's produced these two figures that we just talked about. The first is the sky map, so we've again made a histogram with the photon counts as a function of galactic latitude and galactic longitude, and you can see the counts go from our two defined bounds, which are 50 and 10,000. The peak bin actually is up closer to 10 to the 5, as I mentioned, but then it starts to blow out the scale so you can't see other things as well. And you can see why we might be interested, for instance, in getting rid of this pulse, because it's just totally dominating everything else by orders of magnitude. You can see that there's maybe a little source here, a little source here. If there's a source here, you just have no clue. So we want to get rid of it if we can. And just to emphasize this, I've also plotted here in figure 2 this line right along here of galactic latitude, each galactic longitude for a fixed galactic latitude of about minus 3.15. And so here you can see Vela pulsar again up around 10 to the 5 here at its peak counts, and then coming down to the plateau of just a bit south of the galactic plane. And here's that little blob that we mentioned earlier. Again, if there's anything here that's not the Vela pulsar, well, we'd be looking for a tiny little signal on this huge background. So it'd be pretty ideal if we could get rid of it. And that's what we'll talk about next. Okay, now that we've seen that we want to possibly turn this bright pulsar off, or conversely, if we're interested in studying the pulsar, be able to look at its pulse profile and gamma rays, we need to find a way to map between pulsar spin phase, which, pulsars are rotating neutron stars, so every rotation they go between 0 and 2 pi radians, or we normally normalize that to an interval of 0 to 1 and call it the pulse phase or spin phase. We need to map that spin phase to every single photon. The Fermi-Lat is able to timestamp the photons that it receives with very high precision, other than about 300 nanoseconds. So we can do this after the fact, rather than having to do it in real time, which is often what radio telescopes have to do. Before we get into software that does this, let's take a quick look at the ephemeris we're going to use. And this ephemeris is what tells us how to map between the spin phase and the actual time as recorded by a very precise clock on Earth, or in our case, a spacecraft. So this is an ephemeris that I created about a year ago for the Vela pulsar, and it has a number of parameters that are needed in order to do this mapping of spin phase to time on the Earth. This just tells us a name for the pulsar, but it's very important to know the position in order to figure out how to correct for the motion of the Earth around the Sun, which affects the delay and the pulses that we receive. These parameters here, f0, f1, and f2, describe the actual spin frequency and its first and second time derivative. So Vela spins 11.188 times per second, or hertz, and then these tell you how quickly its rate of spin is changing. Some of these other things won't worry about as much. This tells you roughly how many electrons are between us and the pulsar. That's relevant at radio wavelengths. Here is its motion through the sky, proper motion. It does have a well-measured parallax. Vela glitches, which means that it has a sudden change in its rate of rotation. These are tabulated here. And the other thing that's relatively important for us, besides all these parameters that are not all that important for gamma rays, are these so-called wave terms. Vela, because it's a young pulsar, is not a very good clock. It tends to wobble a bit in its spin frequency in a fairly random process. So we have to solve for that process, and we encode that timing noise in a series of sine waves, so-called fit waves, whose parameters are given here. So this is just the amplitude of a sine and cosine with this particular frequency, which is given in days. So you can see it's a relatively long wavelength, about 1 over a decade, and then these are higher and higher frequency harmonics. Again, just to model this timing noise, which is interesting of its own right, but we don't want it in our ephemeris, in our data. So this ephemeris will correct for it. Now that we have an ephemeris and we have our data, there are a couple of different tools we can use to do this mapping between photon timestamps and spin phase. One is called PINT. It's the most recently developed pulsar timing package. It's being done by the Nanograv pulsar timing array. It's implemented in Python, and the philosophy is kind of that you treat it like a library, build your own programs around it. An older program called Tempo2 was written more as a one-stop shop, and there are various plugins that have been written for it to accomplish specific tasks, like, for instance, phasing up Fermi photons. Today we're going to use Tempo2. I can recommend them both. Tempo2 is just a little bit more convenient to show you in this time-constrained format how to do things. So if we want to phase up our photons, let's again look at our ingredients here. We've got a FITS file, which has our data, Vela merged FITS, an ephemeris, which we just looked at, which gives us the mapping. And this is the spacecraft file, which we haven't seen recently, but that we downloaded at the beginning of this tutorial. And it has this rather cumbersome name. I would typically rename it Vela ft2.fits, but just to make sure you know where it came from, I've left it with its original name. So to do the phasing, it's pretty simple. We're going to use Tempo2. And as I mentioned, there's a specific plugin to do this task. It's called the Fermi plugin, written by my colleague Luca Guillemot. And we're going to tell it which data to use. So the FT1 file is Vela merged. The spacecraft file is this pretty cumbersomely named thing. And then we need to tell it an ephemeris. And this rather obscure command F tells us that we're going to, or signals the program that the upcoming thing is an ephemeris. And then the last thing we need to do is tell it that we want to add the resulting phase that it calculates to the FT1 file, so we can use it in the future. And then I'm going to put this here, which speeds things up a little bit by moving the FT2 file into memory rather than accessing it on disk. So let's give this a run, and it's going to take a number of minutes to do this, so we'll come back when it's done.